All right, welcome back, calculus students. Today we are going to do, this is going to be a quick one. We're going to talk about the area of a polar region, or the area bounded by a single polar curve. So let's just quickly review this right here. Remember what this was called? That's called a sector. So from, I don't know, 9th, 10th grade, area of a sector, it was 1/2 of r squared theta. 1/2 times theta times r squared. So when we try to find the area of a polar, it's very similar to when we use the rectangular coordinate system. Like when we added up all of our rectangles, remember that? We took a whole bunch of rectangles and we added them together, and we had the limit process that created the area. Well, the polars are going to be very similar in nature, but we're going to be adding up a bunch of sectors. So if you think about it, the angle between these, we'll call that our delta theta. So as our delta theta gets smaller, we're going to be adding up a bunch of area of sectors, and the more areas of sectors we add together, the closer our delta thetas are going to get, and we're going to create, or we're going to be able to calculate the area. Now, luckily for you, we don't have to do the limit process on this, but that's kind of the idea of how we're going to find the area. So if you go through this kind of goes through the limit process. You know, if you want to take a look at that and the partitions there. But the bottom line is when it comes down to it, this is the formula that you need to know. So it's very similar to this one. Area equals 1/2 r squared theta. The area in polar coordinates is 1/2 r squared, because isn't our equation in polar written in r form, r equals. So there's our r squared. And then our delta theta, our change in theta. And in between two angles, our lower limit and our upper limit. Okay? And just know that the difference between them has to be less than 2 pi. Okay? So you can't go from 1 pi to 10 pi. It's not going to work. But let's just take a look at the area of one petal of this rose curve. As I've told you in the past, you're not going to have to graph on the AP tests. You're not going to have to graph, but you do have to understand how the polar graphs behave. And I did put several reviews on the website for you to take a look at if you don't remember from last year. But we have a 3 here and we have a 3 here. Any ideas what those 3's represent? Well, this 3 here, let's take a look. Let's just make a little table here. Theta r. If we have 0 radians and our r is 3 times the cosine of 3 times theta, that's going to be 3 times the cosine of 3 times 0. And what's the cosine of 0? Well, that's 1. So 1, 2, 3. That's where we start. And we're going to go in this direction, you recall. And wouldn't you agree that that is going to be half of one of our petals? So if we can find this area, then we're going to be able to find the area of one of our petals. And we don't even have to know, what the rest of the graph looks like. If we take the area of, let's just shade that in here with the blue. Okay. We started here. It's 1/2 the integral of our r, which is cosine 3 theta squared, so all of that squared, times d theta. Well, that's the easy part. The hard part is coming up with our upper and our lower limits. Well, this is where we start. Okay, well, where did we start? We started at 0 radians. Okay, well, where are we going to end? That's the question. Where are we going to end? Well, I'm not really sure, but I know that from here, the theta from here to here is going to be something. So I can actually calculate that theta. So basically what you're trying to figure out is what is the theta when it gets back to the pole? So what is the theta when your radius is 0? A lot of times they give it to you, but let's go through and figure out what our theta would be when we get to this pole. So that means your radius is equal to 0. So we have 3 cosine of 3 theta, which gives you the cosine of 3 theta equals 0. And if we go back to our solving trig equations with a triple angle, whose angle has a cosine of 0? Well, if you remember our little trick, your angle is going to be at pi over 2 and at 3 pi over 2. That's the angle when we get back to the pole. And if you remember, when we have a triple angle, we had to keep generating 2 more revolutions, so we had 3 revolutions in all. Well, again, I'm trying to figure out what my theta is when I get back to the pole. So what is my first theta when I get back to the pole? Well, that's going to be pi over 2 divided by 3. That's going to be pi over 6. So this angle right here is theta equals pi over 6. So can I integrate this from 0 to pi over 6? Would that give me the answer that I'm looking for? Well, no, it wouldn't. But it would give me half of the area of my petal. So how about I just double it, and I go from 0 to pi over 6. If I integrate from 0 to pi over 6 of my r squared d theta, that is going to give me the area, because this right here will give me the area of the blue shaded. And if I double it, I know that that's going to give me the area of one petal. Now the nice thing is, 2 times a half is 1. That's one nice thing. And the other nice thing is that this problem is either a set up but do not integrate, or it's a calculator problem. We're not going to have to integrate this by hand. So it could be like which one of the following is the integral of the area of a petal. So they could have it like this. They could potentially square the 9 and put the 2 here. They could rewrite it. Or it could be a calculator problem. So if I were you, I'd pause the video right now and practice typing that into our calculator and make sure you can come up with the 2.356. Or you can try that later. That's our first example. Let's take a look at our second and last example. It says, find the area of the region lying between the inner and outer loops of our limacon, who knows what Mrs. Greer called it, or Mrs. Watterson. But I call it, I believe it's a limacon. So they want us to find this pink shaded region here. Well, they're nice enough to tell us that it goes through the pole at pi over 6 and 5 pi over 6. But again, what if they don't tell us that? First of all, it's always nice to know where we start. Where does this graph start? Well, again, let's go back to just like before. Let's plug in 0 for our theta. So we have 1 minus 2 sine of theta. What is our R value when our theta is 0 radians? Well, the sine of 0 is 0, so we end up getting a radius of 1. So this is our starting point right here. And it says that we get to the pole at theta equals pi over 6. And it goes this way. And again, if you don't recall how polars behave, you can look at some of the review videos that I requested that you watch. We're going to get back here, back to the pole at 5 pi over 6. But again, what if they don't give that to you? Are you able to calculate that? When are you back at the pole? When is your radius equal to 0? So that's going to be a -1 equals a -2 sine theta, or when sine theta equals 1/2. And from our unit circle, sine of theta is equal to 1/2 at pi over 6 and 5 pi over 6. So our good trig skills match the picture that's given. Okay, however, if I go to set up the area of this, and I go 1/2 the integral, okay, and I go from, let's say, the start of the first time we get to the pole to the second time we get to the pole. So let's say I go from pi over 6 to 5 pi over 6 of my R value, which is 1 minus 2 sine theta squared d theta. What's that the area of? Well, that's the area of the inner loop. That's this area right here. So that's the inner loop area. That's not what they asked me for. They asked me to find the area of the region lying between the inner and the outer loop. So we need the pink. Well, the only way to find the pink area is to take the whole entire area and subtract this green, this inner loop. So the question is how are we going to do that? How are we going to find the whole area in here? Well, when's the first time you get to the pole? Isn't that at 5 pi over 6? So let's do the whole entire one. Let's, I'll just use blue again. The area of the entire, or the whole thing, is 1/2. Well, the first time I get to the pole is at pi over 6. And, I'm sorry, yeah, this inner loop right here, this is pi over 6 to 5 pi over 6. So what I want to do is I want to use the 5 pi over 6, not the pi over 6. I want to use the 5 pi over 6. Because when I get to the 5 pi over 6, I'm right here. And then I'm going to go all the way around. And if I can figure out what that is, that would give me the entire area, the pink and the green all together. So if I start here at 5 pi over 6, what is the angle all the way back to here? Well, that's a little tricky, but we can figure it out. Remember that this right here is where we started. That is theta equals 0 radians. Well, isn't that also, if I'm going all the way around, when I get to here, isn't that also theta equals 2 pi radians? But I need to go a little bit more. And how much little bit more do I need to go? I need to go another pi over 6. So if I get to here, my angle, my theta, or actually it would be what, beta, up to this point would be 2 pi, plus a little bit more to get to here. So it's going to be 2 pi plus another pi over 6. That will give me my upper bounds. So that is 1/2 the integral of 5 pi over 6. And what is 2 pi plus pi over 6? 12 pi over 6 plus 1 pi over 6 is 13 pi over 6 of the equation of my polar graph. And that gives me the entire area. But again, that's not what they're asking me for. They want the pink. So the area lying between the inner and outer loop would be all of this minus all of this. So that would be 1/2 5 pi over 6 to 13 pi over 6 of 1 minus 2 sine of theta squared d theta minus 1/2 the integral of pi over 6 to 5 pi over 6. I'm going to run out of room here. 1 minus 2 sine theta squared d theta. Okay. Kind of like back in algebra when we took the area of a circle and then we subtracted the inner circle to find this shaded region. Kind of the same concept. So this is the area of all of it, and this is the area of the inner loop. Now again, the nice thing is, set up but do not integrate most of the time. Okay, if it is this, if it's not a setup and do not, they are not going to make you do this by hand. It would be a calculator problem that you could type into your calculator. But this one's a setup and do not integrate. Now they could have it, maybe have the 1/2 pulled out. So you're just going to have to pick which one of the multiple choice looks is the same as yours, and a free response. As long as it's right, it's right. All right, and that's area of a polar curve.